Hello everyone. In this video today, I am trying to talk about duality in electrical circuits. What do we mean by duality? And given a circuit, how do we construct its dual? And what is the importance of this? These are the things that I am going to address in this video. If we look at the statements of Kirchhoff's laws, which are 2 in number, we almost see word for word with voltage substituted for current and independent loop substituted for node pair, etc. So one tends to find similarities between Kirchhoff's current law and Kirchhoff's voltage law. Likewise, if we can write the integral differential equations, they appear similar in nature. How do we understand this? Let us try to consider 2 circuits, 2 networks for the concept of understanding duality. Let me write the circuit. I will write an RLC circuit, a series circuit. Okay, this is my R. I will put an L in series. And I will take a capacitor, connect all the 3 elements in series, and would put a voltage source. Alright, this is my resistor R. I'll try to make a little colorful. RLC. This is my V of T. And let me say that this is my current, I, in the loop or the mesh. This is my one figure. This is my figure A. I will call this figure A. I will make one more circuit which will have a current source instead of an voltage source. In the second network, I possibly take a current source. Now I will try to put the 3 elements across this current source. R, I'll put an inductor, I'll put a capacitor, I'll connect everything in parallel. Now this network has got a node pair. I'll take the other color perhaps. This source, I will call it as I dash of T. I'll put an arrow underneath this. This is my R dash, this is my L dash, this is my C dash. This network has got node pairs. Let the potential of this node be V dash, whereas I will take the other node as the datum node. This is my figure B. Alright, so we have 2 figures, we have 2 circuits. And we can always write KVL equation for figure A and KCL equation for figure B, which are convenient. Okay, one is based on the mesh current analysis, another is based on the node voltage analysis. Let us try to write the equations and later on talk about the similarity of the equations. Alright, so if we write the integral differential equations for figure A, what is it we get? What do we mean by integral differential equation? They talk about the instantaneous values. Alright, so they talk about the instantaneous values or the quantities at a particular instant. So V of T, the voltage that is applied to the network, should be equal to the sum of the potential differences appearing across various elements. That is what is our KVL is about. It is sum of E equal to 0 in simple form. Okay, the summation of all the potential differences should be equal to 0. So V of T, the applied voltage, should be equal to, if I can write the equation, it is R into I. That is the potential difference across the resistor. Across the inductor, I write the instantaneous voltage as L di by dt. And across the capacitor, the potential difference that would occur is 1 by C integral I dt. This is the equation I get for figure A. Alright, I will try to reduce it in size so that I manage the space. little and I'll push it here. Okay, this is my equation 1. I'll call this equation 1. This is my equation 1. For figure 2, I will similarly write an equation. How do I write? It is on KCL. The principle is KCL for this network. Okay, the current that enters the node, that is I dash of t, is equal to the sum of the currents that would flow in various branches. The current that is flowing here plus the current that flows here plus the current that flows here through all these branches. That is equal to, if I can write, this is V dash of t divided by R. Alright. So it is conductance times voltage, current equal to, I suppose, a small trivia, because people are familiar, V is equal to I into R. This form people are familiar with, right? I into R. So whereas if I want I is equal to V by R. So that's what we have written here. V dashed by resistance is the current through the resistor. Alright, plus what is the current through the inductor? Current through the inductor now is equal to 1 by L dash, inductor L dash, integral V dash of t, or I can even skip this t because I have not written t there, V dash times dt plus C dash dV dash by dt. This is my second equation. Now again I will shrink it a bit, take it here, and I will call this equation 2. Okay, so we are able to write two equations for the two networks. So we can say that there is a similarity between these two equations. This similarity with all the implications is what we term as duality. Okay, if we can look at these two equations, we find parallels, we find similar quantities, right? So these two networks are completely different in physical appearance. However, inspection shows that the equations that are obtained for these two different equations appear similar. So how do we define duality? So the word duality, or the principle of duality, is that the solution of one equation is also the solution of the other equation. Or in other words, if we look at these two networks, these two networks are said to be duals of each other if KCL of one network is similar to the KVL of the other network. That's how we define duality. So if we can compare the two equations, they appear similar. Hence figure A is a dual of figure B, or vice versa. Figure B is a dual of figure A. The roles of currents and voltage in the two networks have been interchanged. That is what is happening. But we have to remember that there's a word of caution. One network is not equivalent of the other in the sense that one can replace the other. You cannot do that. Okay? So, however, by comparing the two networks, what we can write is, we can draw some analogies. So, if we can write the analogies, what we can do? So, the analogies we can write, analogous quantities. Analogies are analogous quantities. If we can write, what we write here is R into I equal to 1 by R dash, I'll have to put R dash here, 1 by R dash into V. From the two equations, we are simply comparing the two equations, right? This is one. Now, the second thing is, if we can write L di by dt in the first equation is analogous to C dash dV dash by dt. But we cannot put equal to actually here. we can say the analogous quantities are this and this and this. They're analogous. So I will do this. I have done this correction. This is 1 by C integral I dt and 1 by L dash integral V dash dt. They are all analogous quantities. Okay, so they're analogous. You should understand the meaning of analogy. Okay, so if we want to write the dual pair, the dual pair can be obtained like this. So from this, what we deduce is dual pairs. That means what is a dual element? Okay, what is the dual of a particular element? Or what two elements would form a dual pair? That is the question we are now facing. What two elements would be called a dual pair? If we look at these two, this analogy, we can easily say wherever we have R, it will have a dual of 1 by R. R is replaced by 1 by R, then it becomes a dual. Okay, and L and C. I'm dropping the dash, the what do you call L dash, L and L dash, I'm dropping the dashes here. Okay, I'm simply writing L and C, that is a dual pair, and the third dual pair that we can write is I and V. That the loop current, we can say the loop current and node pair, they are duals of each other. Node pair, they are duals of each other. All right, and if we can see that a short circuit can be a short circuit and open circuit, again a dual pair. Voltage source, we can see, and current source. As a dual pair, right? So we are able to find out what are the dual pairs. That means if you have a resistor in the primal network, invariably we call this a primal network. There is another terminology. This is a primal network. It doesn't matter even if you do not know. This is a primal network and this is a dual network. And vice versa. If figure B is a primal network, figure A is a dual network. So one is the dual of the other. So we try to deduce the dual pair. Okay, what next? What do we have further? The question is, if a network is given, is it possible for us to obtain its dual network? And if so, how? There is a step-by-step graphical constructive method for finding the dual of a given network. There is a method. So we will simply follow that method and algorithm and arrive at a dual network. But in the process, we have to remember this dual pair. This dual pair which we have written has to be remembered. Okay, so I'll make another table so that the dual pair can be properly remembered. Okay, so I will make a table here. Maybe I'll write a primal element and its dual element. We will simply make a table. Okay, so if the primal element is resistance, I will write it in symbols. I will not write elaborately. If the element is resistance represented by R, the dual element is 1 by R or G. If this is in ohms, R in ohms, 1 by R is in Siemens or in Morse. All right. Now, if there is a voltage source here, primal element is a voltage source, V of t in volts. It will have a current source and the dual network. Alright, if we have a loop or a mesh, if we have a mesh here, that results in a node pair, a pair of nodes. If there is a short circuit here, that results in an open circuit in the dual pair. If there is an open switch, if there is a switch which is open, we will get a closed switch in the dual network. If we have an inductor in henries, that results in capacitors in farads. Okay, and the capacitor value is 1 by L. If there is a capacitor here in farads, that get replaced by L in henries. This is how we construct a dual network. What is the value of L? If I want to call it an equivalent, the L here is equal to 1 is equal to C. You know the value. We will talk about this eventually. So this is how we understand the dual pair. Now we will try to go ahead with the procedure as to how to construct a dual network. Given a network, how to construct a dual network. That is our next article. We will try to look at that. Okay. So the method to construct the dual network. Let us try to draw a network and let us try to construct its dual. Okay. To take up an example, I will write an example to what is it that we are trying to do? To construct a dual network of a given network. From a given network, how to construct its dual. That is the thing of interest to us. We will try to see how we can do that. Okay. For example, we will try to have a network. I will arbitrarily write a network. Maybe I will try to take a resistor. I will have an inductor. Now I will put a capacitor here. I will make two meshes. I'll put a source. I'll try to write it here. Okay. So the values I'll put, let this be R, let this be L, let this be C, and this is V of t. Okay. So how to construct a dual? So I told you there is a graphical construction technique. We have to follow a technique. Okay. So how to go ahead? So inside each loop or inside each mesh, you place a node. Okay. In a given network, inside each loop, you place a node and give it a number for convenience. Okay. So there are two meshes. So I'll use a color for this. Maybe I'll take up this color. I have put a node inside my mesh 1. I will call this node 1, and I'll put one more node inside this mesh and call it 2. Okay. And now place an extra node which is taken as the datum node external to the network. So my datum node, I will place it here. Okay. This is my datum node. This is node number 3. Okay. Now arrange the same numbered nodes on a separate space. Okay. So what we do is, I'll place it here. I'll place node 1. I'll take the same color. I'll place node 1. I'll place node 2. I'll place node 3. Okay. This is my node 1. This is my node 2. This is my node 3. I suppose it's clear. So initially we have placed a node inside a mesh, and external to the network we place another node. That is the datum node, and we lay all the 3 nodes on a separate space on the same tape. This is my first step. Alright, now we draw lines from node to node through elements in the original network, traveling only one element at a time. Alright, so what we do is we draw lines from one node to another node in such a manner that we pass through one element at a time in the original network. So what I mean is, from 1 to 3, if I can see, I will use my different color, maybe this color. So I will pass through this element from node 1 to node 3. So my V of t lies between node 1 and node 3. And what is the analogous element for voltage source? For voltage source, we have written voltage source V of t is corresponding to I of t in amperes. Alright, so okay, so what we do is, I will try to take my white pencil back so that white is better. Now what I do is, from node 1 to node 3, node 1 to node 3, I will put a current source. This is my entire 3. This is my entire 3. This node is entire 3. Okay, this is my current source. Okay, I will put the arrow upwards because positive sign is upwards. Now I will write this I of t. Okay, this is my I of t. Alright, this is the dual network, dual element. So I am able to do that. Now again I will do the same procedure. I will try to see what I will pass through one element. Okay, from between 1 and 3, I have this resistor R, right? So I will pass from 1, 1 and 3. Between node 1 and node 3, I have a resistor. What is its equivalent? The equivalent is the conductance, or it is R here is 1 by R in Mohs, right? So what I do is, I will take the same, I'll extend this node 1, between 1 and node, I will put this resistor. Okay, the value of the resistor, I can call it as some other element R dash. What is the value? If at all I have to express it in terms of values, this R dash is 1 by R. This R. If it is 2 ohms, here I will take it as 1 by 2, that is 0.5 Mohs. Alright, in terms of numerical values, if at all I want to have it as numerical values. So I am done with that element also. There is one more element between 1 and 2, if we can see. Between 1 and 2, we have a capacitor. So I am traveling from node 1 to node 2 via the element C. Okay. What is the analogous element for capacitor? We've just now saw that the analogous element for capacitor is inductor. So between 1 and 2, I have to put an inductor. I will take my white thing back. Between 1 and 2, I'll move this 2 little further so that I'll get some space. This is my inductor. Now I will take the same color and make this node 2. Okay, so this is my inductor. This I'll call it as L dash. Okay, so what is the value of L dash? If the capacitor, for example, C, if C is 2 farads, L dash would be 2 henries. That is what it means in terms of values. But we are simply seeing the equivalent. So it is, capacitor is replaced by L dash. Now between 2 and 3, if I look at the network between 2 and 3, I'm having this inductor. This inductor, I'm trying to follow a path. This inductor lies between 2 and 3. What is the analogous element of inductor? Is a capacitor. So I will have to replace the inductor by a capacitor in the dual network. This is my capacitor. Alright, this is the capacitor. The value of the capacitor is, I will write it as C dash. What would be the value of C dash? It is equal to L, the magnitude of L. If L is 1 Henry, C dash would be 1 farad. That is what it means. Alright, so this is how we construct the dual. Now you may ask, you have a short circuit between 2 and 3. Like, I can travel like this. Between 2 and 3, I can travel like this. Between 1 and 3, I can travel like this. So that I take all the branches. Like, let me tell you, these are not the branches. These are simple wires. These are simple wires between 2 and 3 between 2 and 3. This is a wire, which is a shorted wire. Short circuit is replaced by an open circuit. So hence between 2 and 3, you don't write anything else. So you take every element of the original network and see where that element appears. Then replace it by its dual. The procedure is to draw lines in the original network and you arrive at the dual network. So what we infer here is we can write that R dash value is 1 by R and your L dash is equal to C and your C dash equal to L and my I dash, I may call this I dash, that is equal to V of t. I will call this I dash. What I mean is, I will take this red back. This is my I dash. Because I have the currents here in the original network. Let me not create any confusion. So if V of t is 2 volt, I dash would be 2 ampere. It is that simple. So this is how we graphically construct a dual network. I suppose the concept of duality is well understood. One can always try out different problems and see if we have understood dual networks. So with this introduction to duality, I suppose I will stop. So all we have to remember is this table. This table is of importance. So we need to remember what each element in the primal network would correspond to a dual element in the dual network. So if we can understand this, one can easily construct the dual network by following the procedure. Okay, so the network constructed in this manner is the dual network of the original network. So now if you can write the integral differential equations of the two networks, they look similar. Okay, this construction may be checked by writing the differential equations of these two systems or these two networks, and one on the loop basis and another on the nodal basis. You will see that they are similar. Okay, I suppose I will stop here. If you have any queries, if you want any more videos to be made on any theoretical concepts, kindly suggest. Thanks for your viewing. See you in my next video.